Hello everyone, and welcome to the tutorial for the 4th axis module for Gearotic 2.0. I'm creating on the screen a small pinion that we'll use as a quick test example on the new module. You'll see on your property screen a Send to 4th axis button under the Send to Workbench. Any selected gear that's appropriate can be sent to the page for processing under 4th axis. When you appear on the page, you're going to find your gears surrounded in a glass blank that is set appropriately sized so that your job is to remove the glass section between the teeth. If you switch through your tools using your favorite list, you'll see that the tool picture changes to give you a visual indication of whether you've got the appropriate tool loaded. Let's take a look at the menu along the top so that we're familiar with everything. We have a return button which takes us back to our normal projects. On the Tools tab you'll find a 4th button to go back to it. You wouldn't want to use the Send to 4th axis button again because you don't want to replace the gear that you've got there. So we'll just hit 4th to go back. Double clicking will give you this view. You are free to rotate at any time and take a look at other views. Next on our menu up top, we've got the next and previous buttons for the tools and quick changes for step over and the Z down per pass setting, as well as speed rate, spindle RPM, plunge, and feed rate. We can change those between tool paths. Then under job settings, we have safe Z, how far up we want the tool to retract. Face width, this is how thick the gear is. This will not change the size of your blank. The blank will always be the size of the gear as you designed it, but there are reasons why you would want to have larger face width, and we'll go into that shortly. Clearance, where we can tell our tools to stay a set distance away from the actual features of the gear itself. Final pass, which can come in useful for getting a skim coat pass of your tool, and then segmentation, which is used to subdivide the involute curves into a set number of passes, and this segmentation setting will greatly control the speed of your cut and how long it's going to take you to make that gear, and we'll go over each of those settings. Next to that we have the output options, and this is where you're going to both post your code and create your code. All gear cutting code under Gearotic 2 at the moment is a function of one or more of 4 different types of paths. We have tangential, routing, root wall, and shaped tool paths so that we can create. Let's take a look at the simplest one, because there's nothing simpler than a shaped tooth pass through a straight spur gear. So I'm going to click on the shaped tool. And you can see what happens is a toolpath immediately appears showing back and forth shaving of a tool which would have to be shaped to the shape of the space between two teeth in order to make any sense. Now's a good time to take a look at the simulation. Beside the Shape Tool button we'll find a simulation panel. We have an off-on button. I'll press on, and when I do you'll see that the tool starts to spin. You can't actually make a realistically spinning tool because the screen doesn't update fast enough, but that lets you know that you're in simulation. You'll get a message in the middle of the screen saying Shaped Cutter Clearing, which tells you what step of the simulation you're currently in. Incidentally, if we look on the right hand side of the screen, we can see our currently selected tool in our tool table. Under that, a message telling us how many paths we have generated. At the moment we have 1, which is generated for an involute cutter, which will come out as in G code as tool number 0. We have toolpath sequencing information under that telling us that the first rotation of the blank will be fly cutting with tool 0, and then there will be no further rotation. So we're going to do this in 1 rotation of the blank, and a current simulator position which is 0, 0, 0, A, 0. And this is where we zero our tool, dead center of the blank, at the very top of the system, right there if you were looking at your 4th axis sideways. Interesting point here that we should look at, you'll see that the face width setting has made us cut the blank, which is 12 millimeters thick, but it's also added enough to each side to ensure that our tool won't hit the sides. The reason that we're not moving even though we're in simulation is we haven't set a speed. So up here next to the on-off button we have a speed. Let's give it a little bit of speed, and now you can see the tool doing what it would do on your 4th axis system. And it moves from tooth to tooth, going lower each time. Now, some people have asked for a unidirectional method of cutting so that they can do climb. Let's turn this off by turning our shape tool off. And let's check the unidirectional button up in job settings and re-click our shape tool. In order to regenerate any toolpath, you simply click it off and click it on again, and it turns orange when there's a valid path in it. So right now our shape tool button is orange, showing us we have a path, and you can see our path has changed somewhat. It now looks boxier, and it's because it's a unidirectional path. Let's turn it on, and you can see the tool now goes across the gear cutting, goes up to safe Z, back, and then across again. So that's your shape tool cut. Both with unidirectional and not. Now, if we wanted to post that at this point, we could hit the Post G-code button. A little dialog pops up which allows us to edit our epilogue and prologue, select a post processor, and hit the post button. And we have an open an editor button so that you could see the path. We'll go into that a bit later. So that's how we do a shaped path. The other three settings, tangential, routing, and root wall, all operate away from the shape tool path. If you hit any of them, let's hit routing for example, and you can now see that the shaped tool has unlit, telling us we have no shape tool. This is because shape tool will not share a G-code file with any of the other three. The other three, you can do all three in one file and mix them up. Now what I have on the screen looks like a fairly complex little file. A little bit confusing, and that's because we have unidirectional still turned on. Unidirectional is very inefficient, and as you can see, it generates a lot of paths because it has to lift up at the end of stroke, come back to safe Z, and all the way back, so it's making a lot of loops. So let's turn it off, uncheck it, and in order to get rid of that, we just uncheck routing and check it again to get a fresh path. And now you can see that we have a routing path. Now the routing path you'll recognize looks a lot like a pocketing, and that's because that's what it is. It's a linear pocket, really. But notice that the bottom pocket is simply one stroke of the tool without moving over. Incidentally, we can make this routing path a little less complex by increasing our step over. My step over here on the screen is 0.5. That's 0.5 millimeters at the moment. So let's move that because we're on a 3 millimeter tool. Let's move that to 2 millimeters. And again, make sure you hit enter if you change any of these settings up here, otherwise they may not take. In order to see what happens, we just turn routing off and turn it back on. And there's our route. Now, you'll notice that there's far fewer cuts, and that's great. You'll notice too that in the cutting process, the idea is to make sure that the tool does not touch the edge of the tooth at no matter what level it's at. The gear is not rotating during this routing. So let's just take a look and see what this routing would look like. You can see it looks kind of normal from the from this angle, but we can rotate it around using our rotating keys and take a look and see what it's doing. And if you're careful and you line it up just so that it's straight on, you won't see the gear going back and forth, but you will see it going side to side. And that'll tell you whether or not it's cutting the gear. And as you can see, it doesn't quite touch the gear. So we have a pretty good clearance pass there. And on the next level, the same thing. But watch this final level, and you'll see that it doesn't move much at all. And that's because if it did, it would hit these curved profiles, these trochoidals on the bottom profile of the fillets. That's probably not a good thing if it were to do that. The program is using graphics to determine these tool paths. While Gearotic Motion originally used the mathematics of an involute gear, Gearotic4th uses the tooth shapes that we generate for the DXF outputs, and it does that so that we could use this type of machining on pulleys, sprockets, and other shapes rather than just evolute gears. So this bottom pass, you may want to get a more than the one pass on it. So it can help for you to give a final pass. If I was to put a final pass of 0.5 millimeter on this, because the 0.5 millimeter takes us above this curvature of the graphics, we actually get an extra little bit of a pass on either side for a more efficient clearing. So you might want to consider having a bit of a final pass. In the end, it can make a bit of difference as to whether or not the trochoidals are cleared out enough for you. So let's take a look at the simulation of this just to see how it looks to us. And you can see that the gear is never touched by the cutting tool, and that's really what's important in clearance passes like this. So that's how we clear out the roots. Let's take a look at another setting, root wall. I'm going to turn off rooting for a moment and just look at root wall. Root wall makes 2 passes for each tooth, and its job is to radialize the root. On any involute, you will start at the tip of your tooth, and you'll see an evolute curve coming down, and it'll come down to a point which we would call the root point. This is where it joins the base curvature, the base circle of the gear. From that point forward, roots, by definition, are supposed to be a straight line from that point to the center of the gear, a radialized root. That's not how it works in practice. Quite often we have trochoidal shapes, such as on the screen here. However, it should always be safe to place a cutting tool on an angle from the edge of this junction of the evolute with the base circle to the root, and it tends to clear up any material which might have been left by a rooting step. Let's take a look at what that does, because this is the first step that uses rotation and at the same time as it moves the X and the Y. And you can see, if we look at it, the gear is rotating one direction and then finding a tangent to the final root point, the final evolute point, and creating a straight line down to gear. Now if I pause it, sorry, I didn't pause that enough. Let's let it go down and grab the next one, and I'll pause it. There we go. And you can see what's going on is that the tool is cutting a straight line from here down through this filleted edge. Now you could use a ball mill if you wish to maintain that radial fillet, or you could just leave it straight if it doesn't make any difference to you, a straight end mill. But be aware that it will chop off this fillet area here unless you are using a ball mill. Okay, so that's how a root path looks like. Now let's take a look at what a tangent path looks like. Here is a tangent path. Many of you will recognize it from the earlier versions of Gearotic. This causes the tool to rub against the tangent of the evolute, divided into however many segments you have set. And up here we have a segmentation of 8, which is making approximately 8 passes. I say approximately because if the tool tries to design a pass outside the shape of the blank, it will chop that one off. So you could be plus or minus 1 on any of these. If I set these to 12, for example, and then cycle our tangential button, you can see we have more passes. Now I'm going to take this back to 8. 8 has been found to be to give a good performance. Okay, let's take a look at what a simulation looks like in tangential mode. I've slowed it down a little bit, and I'm going to tilt this gear up so that we're straight into it again, so that we can see. Now, when you're looking straight into the gear, you won't see the tool go back and forth across the x-axis, so this allows you to see it as if it's frozen in time on each pass. And you can see what's happening is the gear is rotating until its involute curve is at 90 degrees to the tool, which means that the edge of the gear is being shaved on the tool in order to create our waveform. And this is why our tool paths have looked so strange all this time, is because these red rapids, for example, are being shown in their actual trajectory as the a-axis rotates. So watch this tool. You can see we're shaving at the root where we just did a root wall clearance. The tool will then move over to the Y while the gear rotates to find the next tangential spot, and then this will repeat the number of times that we have set in the segmentation, and one by one it'll move across. Now one of the drawbacks of this particular method is, as you can see, the tip of the tool is actually at about the tangential point. This means that you could end up with little lines on your gears and so on, and an aliasing artifact, which is not great. So this method suffers a bit in that it can mark up your gear, but it's good in that it always clears the trochoidal section and will not gouge the opposing face of your gear. But there's a better method, so let's turn off the tangential and select Maintain Depth. Maintain Depth maintains a root depth. As we go around, it lowers itself down to maintain that depth. The danger is it could gouge into a trochoidal if the tool is too large. So you'll notice that it makes a very strange looking waveform, but let's watch the waveform go and you'll get a better idea of what it's doing, even though it looks strange. So here we are shaving the first point on our root. That's straight in with the root at 90 degrees. So here we are shaving the next evolute point, and the tool has actually lowered as it rotated. And if we watch it go through the next tangential point, the tool is now lower again. So now it means in the previous tool path, this tool would have been halfway up the tooth by now. Instead, we're now following along with just the edge rubbing, and this is actually the preferred method of doing a tangential shave, although it produces a very strange looking waveform that you'd swear is broken looking at it. But as you can see from watching the tooth, it's actually shaving it very efficiently, and as you get out towards the tip, you're moving higher and higher on the flute into a stronger part of the flute, which encourages the shape to be even better. We then rotate around, and as you can see, we're moving it up to the next tangent point, and now we'll move with Y, moving off to the Y++ direction as the blank rolls in a negative direction. You might also notice that when the gear blank is rotating negatively, as it is now, it's rotating clockwise. A positive rotation is always counterclockwise. This is because if you picture something at 0 degrees, which would be over here on the right hand side of the gear, and you wanted to angle something up to 90 degrees, that would be a positive rotation taking us to the top, which is a counterclockwise direction. So all rotary axes, when you're looking at the object in the axes, a positive rotation should take you counterclockwise. That's just a convention. So now that we've seen it head on, let's take a look at it sideways, and you can see that all that really happens when we're doing a tangential is the tool is moving in a Y direction to line itself up properly with a tooth. It's then moving in an X direction across, cutting the tooth, and then repeating. Let's just move this up a little faster. There we go. So you can see that the tooth is sweeping back and forth on that trajectory and then moving along. You can pause this at any time by hitting your pause button, and then you can zoom in on the area involved to see if perhaps you're cutting it. And it doesn't look like this tool is going into the gear, so it looks like we're clear. So we would leave it as a maintain depth tangent in this particular gear. We've already seen what a root wall does. Root wall goes and cuts the edge, so we can add a root wall to this. And finally, we can add the rooting. Now, you'll notice I put those in terrible steps, but the system has already reoriented them. Now, if we look on the right side of the screen, we can see we have 3 paths: a rooting path using a 3mm bit, root walls using a 3mm bit, and tangential run using 3. And then we tell, underneath we tell you a sequencing operation, a sequence of the operation. First rotation of the blank, we will be doing rooting with the tool, then straightening, then tangential save, no further rotations. So this is all going to be done in one rotation of the gear. The tool path looks absolutely horrible looking at it. Hard to understand and hard to know what it's doing. But if you hit the simulation button, you'll be able to watch exactly what's going to happen from the posted code when it's done. And if we speed it up, you can see the tool go into all its various positions. First with the rooting, then with the root wall cleaning, and then finally a tangential operation to tangentially shave the teeth. If you're happy with what you see, then you can stop the simulation, hit the post button, and here we can post the code. Now at the top we have an edit, epi, and prologue. These are just ways to edit paragraphs of information that you might want to put at the start and end of your G-code program. These are only used for the 4th axis, as you can see the button up the top says. These are handy for example, setting defaults for your particular mill. We have post processors You would want to use laser, of course. It would be default mill unless you have your own post-processor file that you've made. Again, these post-processor files end in PST. They're in the system folder. You can edit them or create new ones if you wish. They'll automatically appear here if they are. And then we have an open in editor button. So if we say post this, let's post this to a project called Gearotic4th. And now it's asking us for a file name. We'll say Gearotic4th. And it opens up to show us. Now, you'll see that there are several comments in the file. It's telling us that the Gearotic2 made the program. Object name was spur. The job will comprise one rotation of the axis. It will list the tools used. In this case, it'll list 3 tools, but they're all the same as tool 0. The blank size, it will tell us, has a diameter of 56 millimeters and a thickness of 12 millimeters, which is all great. Then it tells us step by step what we're doing. Root clearance begins, tool change to an end mill, and then we get the code for that. When the root wall begins, you'll notice there's no tool change because the system knows that we're using the same tool. So we'll get root wall begins, the code for that, and then we'll get tangential shaving begins, and all the code for that, and then we'll move to the next tooth, and everything will repeat until we get to the end where your epilogue will be printed, and then an M30 for return. Now, something to take note of is you don't need to use the same tool for each step. I have rarely found a reason to change tools, but you may want to change tools. So for example, for the tangential, you may have decided that you want a different tool. I can turn off tangential, switch my tools back to a 2mm tool, hit tangential, and now if we look at the pathing information on the side, it will tell us that tangential is now a different tool. Now you notice that on mine it says rooting tool 0, root walls tool 0, tangential tool 0. This is because my toolbox has not been set up properly. If I look at my 1mm tool here, I've got a G-code tool number of 0. My 2mm tool is also a tool 0, so I should change that to a tool 1, hit apply. My 3 I'll make a 2 apply, and my 0 2 I'll make 3 and apply, just so I can illustrate a point here. I'm going to turn off tangential, turn it on again. Now you can see that on the side of the screen it tells me we have first rotation of the blank. We're going to root it and straighten the root. On the second rotation of the blank, we're going to do tangential saves. It will do 2 rotations of this blank because it doesn't want you to have to change tools between every tooth. So because of that, it will do all of the rooting with its tool first, and then it'll do the tangential. And the system is fully aware of the fact that it needs to do rooting first, so it will make a judgment on what order and what sequence to use depending on the tool paths that you've turned on. A few things that I should mention. First of all, you should always test your programs by zeroing your tool an inch or 2 in the air above your blank and just running it just to make sure that the sequence of operations looks proper to you. It becomes pretty intuitive to you after a few trial runs of your axis as to whether or not your rotation is in the correct direction or whether you're going too deep, etc. It's always best to test like an inch in the air just to be sure. Because these tool paths look pretty complicated. I mean, if you look at the tool paths on the screen now, it would be hard to tell that you're actually cutting an involute gear. And yet, watching the simulation makes it perfectly clear that you are. Okay, that's really all you need to know in order to generate 4th axis tool paths in Gearotic. But let's try a more complex gear so that we're aware of how that works. So I'm going to just destroy this project. I won't save it. I'll go back to circular, and I'm going to select a helical gear. Let's add that pinion. Click it to select it, and send it to 4th axis. So here we have a helical gear. Let's check the select shape tool to see what would happen. And as you can see, it works just as with a straight gear. The only difference between a helical gear and a spur gear is that the A-axis rotates while the X-axis goes. You don't actually move 3 axes at once, as many people would think. You actually just move the X and the A. So let's let it go through and see what it does. Okay, so while it's doing its simulation, you can see again we get shaped cutter clearing, And when the X moves, the A moves as well. Make sure you rotate it around quite a bit to get used to it, because it really can take a bit of rotating around and to get into an axis where you're happy with the helical tool paths. They look very strange. Even the clearance ones can look pretty strange. But if you watch it carefully, as long as it doesn't touch the gear itself, you have a good tool path. If we look at the tangentials and root walls and everything turned on, helicals look very strange, but they do work. So you're encouraged to play around with that until you're happy and satisfied. And so that's all there really is to doing a helical gear. It's the same as doing a spur gear, just with some rotation at the same time. But again, cut it in the air first to make sure that you're happy with what's going to happen. So let's do one gear which is not an involute, so that we get the idea of what happens with that gear. Here is an epicycloidal clock gear. And as you can see, I'm just going to select a routing path here. And as you can see, the routing works just as well, if not better, than on an involute, because the roots are quite radial on these gears. Let's get a larger step over. And there we have it. That looks pretty good and is going to clear the root. It should be obvious to everyone that you've done a good pocket on it. Let's take a look at root walling on these. And you can see that the root wall routine looks like it's going to work pretty good. It's not exactly straight on, because the section, we don't have a base curve on an epicycloidic gear. So the software will attempt to locate the first normal of the tip curve, which is pointing 90 degrees. And once it locates that position, it will pick that as our radial straightening angle. I know that sounds a little hard to understand. Let's try an example on one so that we can see what it does. Now, as you can see, there's our root walling, and it's really just shaving the side of that tooth, which really isn't bad. So that's going to straighten it out nicely. So both routing and root wall work pretty good on epicycloidals. The only one we would have a question on is tangential. So let's watch a simulation of the tangential run on one of these gears and see what it does. Again, this is with maintain depth on, but you can see that the tool is never cutting into the pinion. But we're getting awfully close to the edge of the bottom tooth. In this case, we don't touch it, but this is one of the areas you would want to watch to make sure that you're not gouging the alternate flank when you're clearing something. So this works well for an epicycloidic, which wouldn't have worked in Gearotic motion because it relied on the math rather than the graphic. So you can run these routines on pulleys, sprockets, and so on, but your end result will vary highly depending on what you do and how much you understand what you're doing. So make sure you understand your routing steps, why you're doing a root wall, and whether it's required for that particular type of gear. And then have fun. Please let us know what your experiences are with it. We'd love to hear how it's working out. Obviously, this code will morph over time to take in more types of objects and allow you to cut more gears. Thanks.